So we know how to calculate static pressures in unmoving fluids, but now we're going to talk about measuring static pressures. And one of the oldest and most oldest ways to do that is using something called a manometer. A manometer is a pretty simple device. You just take a glass tube or a tube that you can see through, shaped in a U pattern. One end of the tube is open to the atmosphere or to whatever pressure you're trying to measure. The other end is sealed, and then you pull a vacuum in it. So, and then you fill the tube, not completely, but you put some liquid in it. In this case, it's going to be mercury. Put some mercury in the tube, and what's going to happen is that the pressure from the atmosphere is going to push down on the left-hand side of the mercury column. The right-hand side of the mercury column, of course, is exposed to vacuum, so there's no pressure pushing down. So there's going to be a height difference between position 1 and position 4, where position 1 is the position height of the mercury on the left-hand side that's exposed to atmosphere, and position 4 is the height of the mercury where it's exposed to a vacuum. So that height difference is going to allow us to calculate the actual pressure at the open end. So we're going to go ahead and try to calculate that that height difference for a pressure of 1 atmosphere. So we have a 101,000 newtons per meter squared is going to be our atmospheric pressure. We're going to assume that's what we're measuring. The density of mercury, which we will need, is 13,546 kilograms per meter cubed. That's one of the reasons people choose mercury for the manometer. It's a very dense liquid, so that's it's 10 times, more than 10 times denser than water. So we're going to have a 10 times less of a height difference that we can see, so we can measure larger pressure differences by using a nice dense fluid such as mercury. So we're going to analyze this. We're going to look first at the U portion at the bottom of the tube. So on the bottom of the tube, position 1 here is the top of the mercury column. It is exposed to the atmosphere. So the pressure at this position on the mercury is, the pressure is 1 atmosphere, 101,000 newtons per meter squared. Position 2, the question is, what is the pressure on that side? So it's pretty easy to calculate that just based on kind of looking at the difference between pressure 1 and pressure 3 and pressure 2 and pressure 3. So pressure 3 is at the bottom of the tube. And we know that the pressure at the bottom of a liquid, and it's hydrostatic, again, fluid is not moving, pressure 3 is going to be equal to just pressure 1 plus rho times g times d, where d is that difference in depth between the surface of the fluid and the depth at which we are measuring pressure. Similarly, the pressure at pressure 2 is going to be pressure 3 minus rho, g, and d again. But since we've chosen 2 to have the same position as 1 in terms of height, d is the same, rho is the same, g is the same. That means that the pressure at position 1 and the pressure at position 2 have to be equal to each other. And we know that the pressure at position 1 is just atmospheric pressure at P naught. So we know the pressure in the column right here is going to be equal to P naught. So that's going to allow us to calculate what the actual pressure is, or the height calculation here. How high is that column 4 going to be in order to represent that 1 atmosphere of pressure? So we know that the pressure at 2 is equal to P naught, which is equal to 101,000 newtons per meter squared. And we know that the pressure at 4 plus rho GH is equal to the pressure at 2, right? So we know that if we look at this column here, on the right-hand side, we have the pressure at 4 here, and then we've got the pressure at 2, and it's clear that the pressure at 2 is going to just equal this pressure, whatever the pressure is at 4, plus rho GH, where this, of course, is H, because this is the difference between the column height at position 1 and the column height at position 2, and the column height at position 4. The column height at position 1 and position 4, because position 2 and position 1 have the same height. So that pressure at 2 is going to be 4 plus rho G8, but pressure at 4 is equal to 0 because it's in a vacuum. So that means that the pressure at 2 is equal to rho GH, and we know that the pressure at 2 is equal to the pressure at 1 because that's what we just showed. So we know that rho GH is equal to actually the pressure at 1. And the pressure at 1 is atmospheric pressure. So that's equal to P naught. So that means that H is going to equal P naught over rho G. So it's a very simple way to measure pressures. You just have to know the density of the liquid you're dealing with, make this U tube, and pull a vacuum. So our pressure at our atmospheric pressure in this case, 101,000 newtons per meter squared, divided by density, which we know is 13,546 kilograms per meter cubed, and finally gravity, of course, 9.81 meters per second squared. Those units all check, they're all standard SI units, and H comes out to be 0.76 meters. And you may know this already because a lot of times people report that 1 atmosphere is equal to 760 millimeters of mercury, NMHG, which is millimeters of mercury, and that's a measurement for pressure. And it's based on this kind of manometer reading. So if you expose the atmosphere to, if you expose the open end of this manometer to 1 atmosphere, the difference in height between the low mercury on the left and the highest position of the mercury on the right is going to be 760 millimeters of mercury. And mercury is chosen because it's very dense, and so it will have a smaller height difference than if you chose a less dense fluid. The final thing we should be concerned about is P4 really 0? Because we know that this mercury is a liquid and it's being exposed to a vacuum. A liquid exposed to a vacuum, it evaporates, it boils. So the liquid mercury at the surface of this facing the vacuum is going to boil, and there's going to be a little bit of mercury vapor up into that vacuum. So it's not truly going to be 0. What is it going to be? Well, the pressure in that situation is going to be based on the saturation pressure of mercury at 20 degrees C, assuming we're at 20 degrees C. So at T equals 20 degrees C, we can find that the P saturation pressure for mercury is equal to 0.00018 kilopascals, which is equal to, I gotta move the decimal place to get regular pascals, but so 0.18 pascals. So that's 0.18 newtons per meter squared. Well, that's a very, very small number. It's not 0, but compared to 101,000, that is quite a lot smaller. 0.18 is a heck of a lot smaller than 101,000. So we are in pretty good shape here, assuming that that vapor pressure is actually 0, because mercury has a very, very low saturation pressure. It does not vaporize and go into vapor easily. And so that saturation pressure for mercury is very low. And that's another reason that mercury is a good choice for a manometer.